Hi everyone, in this video we are going to talk about pole and polar with respect to a circle. Let's first take a look at the definition. I have it on the screen. If P is any point in the plane of a circle, then the polar of P with respect to the circle is the locus of the point of intersection of the tangents drawn at the ends of the chords that pass through the point P. The point P is called the pole of the locus or the polar. So as you can see, pole is a point and polar is the locus of a point of intersection. That means polar is a straight line and pole is a point. Now let's try to understand the concept of pole and polar through a diagram. Let's suppose we have a circle like this, and inside the circle I have taken a point P whose coordinates are x sub 1, y sub 1, and then I'm going to draw a chord going through this point P. Let's suppose this is one of those chords. In fact, we can draw infinite number of chords through the point P, but this is one of them. And then I'm going to draw two tangents through the ends of this chord. And the tangents could look like this. And as you can see, the tangents actually intersect at a point. Next, let's draw another chord going through P, and then let's do the same thing. Let's draw two tangents through the ends of this new chord, and let's suppose those are the two tangents. As you can see, they also intersect at a point. And then if we join these 2 points, I mean the 2 points of intersection of the tangents, then we get a straight line, and this is the line which will be called the polar of the point P with respect to this circle. With respect to this particular circle, and for this particular point P, the polar will look like this dotted yellow line. And in fact, you can draw as many chords as you want through the point P, and if you draw the tangents through the ends of each of those chords, you will see that the tangents actually intersect at a point which lies on this particular dotted line, the yellow dotted line. That is the polar of this point with respect to this particular circle. And in this example, we considered point P to be located inside the circle. There are two other possibilities where the point could lie on the circle or outside of the circle. So let's take a look at those two cases also. In the second case, I'm going to consider point P to be located on the circle and then see how its polar going to look like. Next, I'm going to draw a chord through the point P. Let's suppose the chord looks like this, and then I'm going to draw two tangents going through the ends of this particular chord, and of course they intersect at a point. And then I'm going to draw another chord, and again I'm going to draw the tangents through the ends of this chord. In fact, if you think about that one particular end where P is located, on that end the tangent will look exactly like the yellow tangent line that I already have there. And then I'm going to draw just one other tangent through the other end. Now as you can see, all the tangents through the ends of any chords that we can draw through the point P, the tangents drawn through the ends of any of those chords will actually intersect on that particular tangent line which is actually going through the point P. So that particular line will be called the polar of the point P with respect to this circle. That means when the point P is located on the circle, the polar of the point will be the tangent drawn on the circle at that point. And here I have denoted that with a dotted red line. That is the polar of this point P with respect to this particular circle. And that was our possibility number 2. Next, we are going to take a look at another possibility where point P is outside of the circle. Let's suppose you have a circle like this and point P is outside of the circle. Next, I am going to draw a couple of chords passing through the point P. In fact, they will look like secant lines. Here I have drawn one chord, and then I'm going to draw tangents through the points at which this particular secant line intersects the circle, as if I have drawn the tangents through the ends of that particular chord. If you consider the portion of the secant line that is inside the circle, that could be called a chord. And if we draw tangents through the ends of that chord, then the tangent should look like this, and we got a point of intersection there. Now let's draw another chord, and then let's also draw two tangents through the ends of this particular chord. The tangent lines could look like this. So now we have 2 points of intersection of the tangents, and if we join them together, that will give us the polar of this particular point P with respect to this given circle. And the polar is going to look like this. This yellow dotted line, that is the polar of the point P with respect to this particular circle. So when a particular point is given and a particular circle is given, then the polar will be exactly like this. No matter how many chords you draw, every time you will see that the tangents drawn through the ends of those chords will always intersect at a point that lies on this particular dotted line, which is the polar of this point P. So as you have noticed, when P was inside the circle, the polar was outside. When P was on the circle, the polar was also on the circle, meaning it was a tangent touching the circle. And when P is outside of the circle, the polar goes through the circle, meaning the polar now intersects the circle, as if the polar is inside the circle. Next, we are going to see how to derive the equation of the polar. We are going to review each of the three cases. So let's go to the first situation. Here on the diagram, let's assign a few names here. I have assigned names R and S for the two ends of one of the chords here, and the point of intersection of the tangents going through the ends of this chord has been named as point Q, and I am assuming the coordinates of point Q, H, K. Let's assume that the equation of this given circle is like this. I am taking the general form of the equation of a circle. Now if you look at the diagram carefully, you will realize that RS is nothing but the chord of contact of the tangents drawn through an external point Q. Even though we did the drawing completely opposite way, but now for the sake of deriving the equation of the polar, let's consider that Q is an external point and we have drawn two tangents to the circle and the chord of contact is RS. So what would be the equation of RS? Well, we already know the equation of the chord of contact is like this. I have already done separate video on this topic. I have shared the link in the description. Feel free to watch that video. Now if you think about it, this chord of contact also passes through the point P whose coordinates are x sub 1, y sub 1. So if we satisfy this equation with the coordinates of point P, then it's going to look like this. Now from this equation, if we try to convert it into a locus, then all we have to do is we have to replace the h by x and k by y. So the general locus of point Q could look like this: x sub 1 times x plus y sub 1 times y plus g times x sub 1 plus x plus f times y sub 1 plus y plus c equals 0. So this is the locus of the point Q. And now if you think about it, the locus of this particular point actually represents the polar of the point P with respect to this circle. That means we have already arrived at the equation of the polar of point P. So in this case, please note that point P is a given point. That means you will be provided with the coordinates of the point P, and also you will be provided with the equation of the circle because it's a given circle. So the equation of a polar can be determined only when we have been provided with the equation of the circle and the coordinates of the point P. Let's see how we can derive the equation of the polar in the second case. Here again, I'm going to assign a few names. One of the chords would be PR, and Q is the external point for the purpose of derivation. Let's assume the equation of the given circle is like this, and then the equation of the PR chord, which could be considered as the chord of contact with respect to an external point Q. So this is the equation of chord of contact when tangents are drawn from an external point to a given circle. Now this particular equation also should satisfy the point P because we know that this particular chord of contact also passes through the point P. So if we satisfy this equation with the coordinates of P, I mean x sub 1 and y sub 1, then our equation would look like this. I have it on the right hand side, and to convert it into a general locus of the point Q, we are going to replace h by x and k by y. Then it would become a general locus, and this is the equation of the locus of Q. So essentially this is the equation of the tangent drawn through the point P, and in fact that is the polar of the point P with respect to this particular given circle. Let's do the same thing for the third case. Let's assign a few names here, and let's assume the equation of the given circle is like this. And here again, what would be the equation of the chord of contact? Well, it would be like this, and then this chord also passes through the point P, so the coordinates of P should satisfy the equation of this chord of contact. And if we satisfy with the coordinates of point P, our equation is going to look like this, which is on the right hand side. And then to convert it into the locus, we are going to replace h by x and k by y. So this is the locus of the point Q which lies on the polar. That means this is the equation of the polar of point P with respect to this particular given circle. So then in general, the equation of polar for a given point with respect to a given circle is like this. I hope the derivation of the equation of polar made sense. Next, we are going to talk about a couple of properties of pole and polar. The first property that we are going to discuss is the reciprocal property. It says if polar of a point P passes through another point Q, then the polar of point Q would also pass through the point P. So if P's polar passes through Q, then Q's polar would pass through P. And in that case, P and Q will be called conjugate points. Next, we are going to see the proof. Let's suppose the equation of the given circle is like this. I am taking the general equation. Now if P's coordinates are x sub 1 comma y sub 1, then the equation of the polar of P would be like this. We just saw the derivation at the beginning of this video. So this is the equation of the polar of P with respect to this given circle. And if we assume that the polar of P passes through the point Q, then Q's coordinates should satisfy this particular equation. And if we satisfy this equation with Q's coordinates, then it's going to look like this. And this is called condition of conjugacy of 2 points with respect to a given circle. So if the 2 points are P and Q, whose coordinates are given, and also the equation of the circle is given, then this particular condition will be called the condition of conjugacy of the 2 points P and Q with respect to the given circle. That means if this condition is satisfied, I mean the left hand side quantity is equal to 0. If this condition is satisfied, then we can safely say that the 2 points are actually conjugate points with respect to a given circle, of course. Now what would be the equation of the polar of the point Q? Well, it can be written like this. This will be the equation of the polar for the point Q. And then if you look at this equation with the condition of conjugacy, it looks like the equation of the polar of Q has been satisfied by the coordinates of the point P, which are x sub 1 and y sub 1. Take a look at it carefully and think about it. The condition of conjugacy looks like it is the equation of the polar of Q when satisfied by the coordinates of the point P. So then you can clearly see that the polar of Q would also pass through the point P, because if we satisfy the equation of the polar of the point Q, then it looks like the condition of conjugacy and that will be satisfied. That means we can safely say that yes, in fact the polar of the point Q would also pass through the point P. That means the equation of the polar of point Q satisfies the coordinates of the point P, and we can clearly see that through the condition of conjugacy. And I have noted the same thing here. I hope the proof made sense. Next we are going to see how to find the pole of a given line with respect to a given circle. Let's suppose the equation of the given straight line is ax plus by plus c, that's an uppercase C. So ax plus by plus c equals 0, that's the equation of the given line. And the equation of the given circle is the general equation x squared plus y squared plus 2gx plus 2fy plus c equals 0. Now we are going to see how to find the coordinates of the pole from these two pieces of information. Let's suppose the coordinates of the point P is x sub 1 comma y sub 1, and we are going to try and find out the values of x sub 1 and y sub 1. That is our task here. Now what would be the equation of the polar of this particular point P with respect to this given circle? Well, it can be written like this, and if we remove the parenthesis, it can be written like this. And then if we reorganize the terms, we bring the x terms together and the y terms together and the constant terms together, then the equation can be written like this. And let's call it equation number 1. And the given equation of the straight line is like this. Let's call it equation number 2. Now these two equations are exactly identical. I mean both of them represent the same straight line. So when two equations represent the same straight line, then we know that the ratio of the coefficients of x will be equal to the ratio of the coefficients of y, and that will also be equal to the ratio of the constant terms. So what would be the ratio of the coefficients of x between these two equations? I mean equation number 1 and 2. Well, the ratio would look like this, and that will be equal to the ratio of the coefficients of the y terms, and again that will be equal to the ratio of the constant terms. And from here we are going to somehow solve for x sub 1 and y sub 1. So let's try to solve. First I am going to take the first portion and the last portion. I mean I am going to take the first ratio and the last ratio, and from here if we cross multiply, we are going to get something like this. And then let's remove the parenthesis, and from here let's bring all the x terms together, and then let's try to bring all the terms with x sub 1 together, and then y sub 1 terms separately, and then constant terms separately. The equation can be written like this, and let's call it equation number 3. So here we have an equation in x sub 1 and y sub 1. Let's try to come up with another equation. To come up with another equation, I am going to take the first two ratios, which looks like this, and then we are going to cross multiply. It would look like this, and then we are going to remove the parenthesis, and then we are going to rearrange the terms. Our equation would look like this, and let's call it equation number 4. So we have two equations, which are equation number 3 and equation number 4. They are equations in x sub 1 and y sub 1. We have two unknowns, two equations, so we can easily solve for x sub 1 and y sub 1 from these two equations. Let's multiply the equation number 4 by f, then we get something like this. Let's call it equation number 5, and then let's add equation number 3 and 5. and after addition we are going to get something like this. Here we have an equation only with x sub 1 as the unknown. So from here we can easily write down the value of x sub 1, and this is the value of x sub 1. Next, let's also try to find out the value of y sub 1. The equation 4 was like this, and from here let's see what would be the value of y sub 1. If we plug in the value of x sub 1, then a times y sub 1 would look like this, and then let's simplify a little bit. The equation would look like this. Upon further simplification, the right hand side will look like this, and then you can see there is a common factor a in the numerator, so we can write it like this. And then if we divide both sides of this equation by a, then on the left hand side we are going to be left with just y sub 1, and on the right hand side it will be the entire quantity without the multiplied a. So from here we can say that the value of y sub 1 will be like this. And then we are going to see a special case for the values of x sub 1 and y sub 1. If we consider the circle to be centered at the origin, I mean if g is equal to 0 and f is equal to 0, then the value of x sub 1 will simplify to something like this. And then in place of c, I am going to use negative r squared, because you know that r squared is equal to g squared plus f squared minus c, and when both g and f are 0, then r squared will be equal to negative c, and from here we can say that c will be equal to negative r squared. So in place of lowercase c, I am going to use negative r squared in the numerator. Then the value of x sub 1 would look like this. It would be negative a r squared over c, that's the uppercase c from the equation of the straight line. And similarly, what would be the value of y sub 1 when the circle is centered at the origin? There also the value of y sub 1 would simplify to something like this. It would be negative b r squared over uppercase c. So when the equation of the circle and the equation of the polar are provided, you can clearly see how we can easily calculate the coordinates of the pole. Next, we are going to take a look at the property number 2. The property number 2 is also called the reciprocal property. It says that if the pole of a given line with respect to a given circle lies on another line, then the pole of the second line also lies on the first line. Like how we saw in the property number 1, where if the polar of a point passes through a second point, then the polar of the second point would pass through the first point. Similarly, here we are saying that if the pole of a given line with respect to a given circle, of course, lies on another line, then the pole of the second line would also lie on the first line. So now let's see how to prove it. Let's suppose the first line's equation is like this, and the second line's equation is like this. And also let's suppose the equation of the given circle is like this. So those are the three pieces of information already provided. We have to prove that if the pole of the first line lies on the second line, then the pole of the second line would also lie on the first line. Let's suppose the pole of the first line is the point P whose coordinates are x sub 1, y sub 1. We are just simply assuming. And also let's assume that the pole of the second line is the point Q whose coordinates are x sub 2, y sub 2. Now from the given equations of the straight line and the circle, let's try to find out the values of x sub 1 and y sub 1 that we just saw a minute ago. The value of x sub 1 would look like this. I am simply using the formula that we just derived, and similarly the value of y sub 1 can be written like this. Next, let's also note down the value of x sub 2 and y sub 2 using the same formula. They would look like this. I have it on the right hand side. Now, with the assumption that the pole of the first line lies on the second line, we have to prove that the pole of the second line would lie on the first line. So now we are going to create this condition where the pole of the first line would lie on the second line. So I have noted here that x sub 1 and y sub 1 should satisfy the equation of the second line, because those are the coordinates of the pole of the first line, and with the assumption that they lie on the second line, that means x sub 1 and y sub 1 should satisfy the equation of the second line. The equation of the second line is like this, and then let's plug in the values of x sub 1 and y sub 1. Our equation would look like this, and then we are going to simplify. Now if we remove the parenthesis and we do the addition, and then we multiply both sides by that a sub 1 times g plus b sub 1 times f minus c sub 1, then our equation would look like this, and we get something like this. So this is the condition of conjugacy, that if two lines are conjugate lines, then the condition of conjugacy would look like this. Previously we have seen the condition of conjugacy of 2 points, and here we are seeing the condition of conjugacy of two lines with respect to a given circle, of course. Now if this condition is true, then we have to prove that Q's coordinates will also satisfy the equation of the first line. That means we have to somehow prove that Q also lies on the first line. With the help of this particular condition, we will be able to prove that. Now let's see how to prove it. So if this is the equation of the first line, and if we plug in the values of x sub 2 and y sub 2, then we should be able to prove that the left hand side of this equation will be actually equal to 0. And let's try to do that proof. So now I'm taking only the left hand side and we'll plug in the values of x sub 2 and y sub 2, and then we'll prove that this quantity is also equal to 0, which will essentially prove that q also lies on the first line. So let's plug in the values of x sub 2 and y sub 2. The quantity would look like this, and then we're going to simplify it. Upon simplification, the numerator is going to look like this. I'm not going to write the denominator here because denominator is obviously a sub 2 times g plus b sub 2 times f minus c sub 2. That is the denominator. So I have not written that. I am simply going to write the numerator portion after simplification, and the numerator is like this. And then we're going to prove that this numerator is actually equal to 0. That means the entire quantity will become 0 with the consideration that there is a denominator, of course. But if we can somehow prove that the numerator itself is 0, then the entire quantity will be 0. So please assume that there is a denominator under this numerator. I just have not noted it, but please assume that it's there. Now let's see how we can prove that this quantity is actually equal to 0. Well, I'm going to take the help of the condition of conjugacy, which is shown in the pink box there, and I'm going to match this particular quantity with the left hand side of the equation in the pink box. So let's try to match term by term. Now here is a matching term, and here is another matching term, and here is another matching term, and then here is another matching term, and then here is another matching term. Similarly, here is another matching term, and another one, and another one, and we have 3 more to go. So here is another matching term, and here is another one, and here is the last one. So as you can see, in our quantity, the numerator quantity, of course, is actually looking like the left hand side of the equation that I have in the pink box. That is the condition of conjugacy. That means this particular quantity is essentially equal to 0. So now that we are able to prove that the numerator is equal to 0, that means the entire quantity will be equal to 0. That means a sub 1 times x sub 2 plus b sub 1 times y sub 2 plus c sub 1 is actually equal to 0. So we are able to prove that the coordinates of the point q satisfies the equation of the first line. That means the point q also lies on the first line. That means the pole of the second line also lies on the first line. And that's exactly what we needed to prove. I hope the proof made sense. Next, we are going to take a look at one last property. That's the property number 3. The property number 3 says limiting points of a family of coaxial circles are actually conjugate with respect to every circle in the family. I have already created separate video on the topic of limiting points. I have shared the link in the description. Feel free to watch that video. So let's see how to prove this property. Let's suppose the equation of the family of coaxial circles is like this, where k is a parameter, of course. Now for this particular equation, we know that the limiting points will be like this. Now what would be the polar of point p sub 1? Well, the polar of point p sub 1 with respect to this family of circle would be like this, the one in the yellow color. I have noted the general equation of the polar in the light green color, but the actual equation of the polar of point p sub 1 would be what in the yellow color here. And let's simplify that a little bit. It would look like this. And if we bring the x terms together and the constant terms together, our equation will be looking like this. So this is the equation of the polar of the point p sub 1. Next, we are going to try and see if this satisfies the coordinates of point p sub 2. If it does, then our property will be proved. So we are going to take the left hand side of this equation, and then we are going to use the coordinates of p sub 2 and then see if that quantity becomes 0. Then only we can say that yes, in fact, this particular polar also passes through the point p sub 2. So let's take a look at the left hand side of this equation. So next, we are going to take the left hand side of this equation, and then we will be using the coordinates of p sub 2, and that's exactly what I have done. On the left hand side, I have used negative square root of c in place of x, and this is our left hand side quantity of the equation of the polar, and we are just testing with the coordinates of p sub 2, and if we see that this value will become 0, then we can say that yes, in fact, p sub 2 also lies on this polar. So if we simplify the expression, it's going to look like this, and as you can see, the positive lowercase c and the negative lowercase c would cancel out each other, and similarly we have a positive k times square root of c and a negative k times square root of c. They will also cancel out each other, so essentially this also becomes 0. That means we can safely say that the equation of the polar also satisfies the coordinates of the point p sub 2. That means p sub 2 lies on the polar of p sub 1. So we can say that P sub 1 and P sub 2 are actually conjugate points with respect to every circle in the family of the coaxial circles. Now why I am saying every circle? Because we were able to do the proof with the general equation of the family of coaxial circles. So we did not take the equation of a particular circle, we took a general equation of the entire family of coaxial circles, and from there we have been able to prove that P sub 1 and P sub 2, they both are conjugate points. That means they are conjugate points with respect to every circle in that family of coaxial circles. I hope all the steps made sense. Thank you for watching. See you in the next video.